Also in 5.5 and 5.7, there is topics that talk about doubling times and half-life. The doubling time occurs in growth functions, and that means basically the amount of time it takes for whatever it is you're talking about to double. Whereas a half-life is in decay functions, and it's basically the amount of time that it required to end up with half the original amount. Now, there's two situations that you tend to see when you're asked these kind of questions. This first example, example 5, is talking about situations where you have an exclusive formula that's in terms of telling you it's doubling time or half-life. Like for instance here, you know this is a growth function because its common factor is above 1. And because it happens to be a 2, it's a doubling time. So this one would be a doubling time function, and basically that's seen in the function itself. And so when you're looking at this function, it's definitely going to have a doubling time, and the period of time it takes is every 4 hours, because that's when after every 4 values of t, that's when you get an integer. So basically here, the bacteria in this sample, which is what's being represented here, is going to have a doubling time because it's a growth of 4 hours. Whereas down here, you have the number of bacteria in a second sample, and you can see here that you see a 0.5. Keep in mind that you might also see this as written as 1/2 as well. You can see decimals or fractions being used in many of these cases. And because that's 1/2, this is a decay, which means that you're dealing with half-life here, and that half-life occurs, well, here's the period of time, every 9 hours. So this one would have a half-life of 9 hours. Where it starts becoming a little bit more complicated is that not all functions are going to necessarily follow a doubling time or half-life formula where you have the common factor of 2 or 1/2 involved. So that's what this one's dealing with. You have this function here, f of t equals 800 times 0.815, where t is the time in years. You're asked to answer some of the same questions you did before. If it's a growth or a decay, the initial value, the percentage rate of change. And we're not going to spend a lot of time on the rule of 70. It is a nice way of estimating. And sometimes it's pretty accurate. In other situations, it's a bit off. But I did want to talk about it because at this point, that would be the best way to figure out a period of time it takes for that doubling time or half-life. So here, this function here, because this is 0.815, that's under 1, so this is going to be a decay. The initial value, of course, is the constant here, 800. And so the percentage rate of change, this represents 81.5%, but that's the amount that remains after every t years. This is asking more about how much was lost. So if you have 81.5% remaining after a period of time, that means you're losing 18.5%, and that's why the percentage rate of change is a negative 18.5. Knowing the percentage rate of change, not worrying about necessarily whether it's decreasing or increasing, is what helps you calculate the half-life or the doubling time using the rule of 70. And basically, you take this percentage rate as a percentage, 18.5. You don't turn this back into a decimal. You leave it as 18.5%. And you calculate that by taking 70 divided by that percentage rate of change. So it's going to have a half-life because it is a decay function. And if you do 70 divided by 18.5, you get approximately 3.78 years. And so that's the amount of time it takes for whatever this is to become half its original amount. So if it starts with 800 in 3.78 years, it'll be down to 400, and then another 3.78 years it'd be down to 200, so forth and so on. This one here, on the other hand, because you see the 1.214 as the common factor, that's over 1, so this indicates it is a growth. The initial value, of course, is this constant being multiplied, so that's going to be 1,234. The percentage rate of change, since this decimal represents 121.4%, the rate of change is 21.4%. And so using the rule of 70, because it is a growth function, it's going to have a doubling time, not a half-life. And you do 70 divided by 21.4, you get approximately 3.27 months. So after every 3.27 months, this initial value is going to double beyond that. So that much time goes by, you're going to be up to 2,468 and so forth and so on. And in the third one, very similar to the previous one, it is a growth again. But what's different is you have that fraction over 4. And so how do you handle a situation like this? Because it gets a little bit more complicated when you deal with the percentage rate of change, because the percentage rate of change is always per unit. In this case, it would be per hour, and you need to know what that is in order to use the rule of 70. So the initial value, of course, is 625. That's not a really big deal. But the thing is, this is 102.3%, but that's every 4 hours. So I got to figure out what happens per hour. And so the way that you handle this is you need to come up with a unit percentage rate of change. This 1.023 to the t over 4 by your exponent rules is the same thing as 1.023 to the 1/4 power raised to the t. If you put it in terms of just t only, that's going to be now per hour. And so if you take this and raise it, you get about 1.00571016, which is 100.57% approximately, which means it's a growth of 0.57%. Now keep in mind that that's just for reporting up here. When I go and do the next calculation for the rule of 70, I'm going to do 70 because it has a doubling time, 70 over the 0.57, but I would tend to use the other decimal places too, so the 1016 and whatever other your calculator may still have in it. But you would find that the difference is very small. If you keep the decimals or just say 70 divided by 0.57, it comes out to be about 122.8 hours. So this one would take a much longer period of time to have its doubling time than the previous example. But anytime that you have a situation where you have the over 4 and it's not a it's not a 2 out here for a regular doubling time problem, you have to evaluate this and convert it into per hour or per unit, and then that's going to give you the percentage rate of change you need to be using in your doubling time estimation. And so that is the end of this problem, and that is the end of this video. If you have any additional questions, please make sure to bring them up during class.